Hello everyone. What friendly people. I'm not used to that. This isn't normally a friendly place. It's a very serious place, so I appreciate that. Friendly and serious. How are you all? Welcome to the third episode of Science Fiction Becomes Science Fact. Sorry, new glasses. Let's try it up here. We show what great scientific ideas have sprung from the world of books and movies and so on and are turning into fact, although which way they go is a little hard to tell at times. My name is Rod Lamberts. I'm the Deputy Director of the Centre for Public Awareness of Science at the ANU, down the road somewhere. And I'm going to be giving you some information and then wrangling questions at the end of the evening. I'm also the co-host of a fabulous show that's held every month called Kinda Thinky. And if you want to go to Kinda Thinky, and you probably do, you just don't realise it yet, just type kindathinky.com into your web browser and you'll be amazed and dazzled. We look forward to seeing you there as well. I'd like to thank some supporters tonight. The event sponsors tonight are Castro, that's a C-A-A-S-T-R-O, which is the ARC Centre of Excellence for All Sky Astrophysics. Very impressed with that. And the series wine sponsor, even more importantly, I suppose, the people who sponsor the wine all the way through this year's event are the Jira Wines at Jer Station. I'd also like to thank and acknowledge the traditional owners and pay respect to the land on which we meet. The traditional owners are the Ngunnawal people of the Waridjuri Nation. It's upon their ancestral lands we meet today and on which the Academy of Science is built. As we share our knowledge, teaching and learning, and also research practices, I'd like to pay respect to the knowledge forever embedded within the Aboriginal custodianship of the country. I'd like to also welcome our live stream people. I may or may not be staring at them now, but this whole event is being live streamed on the magical internet via the Academy website. If you want to follow along or make comments, you can use the hashtag sci-fi sci-fact. Do people know what I mean by a hashtag? There's a few who don't want to admit it, and there's a few shaking their heads quite clearly. If you're on Twitter, you're all on Twitter, of course. Is anyone on Twitter? There's a couple of hands and one elbow. Okay, if you do want to make some comments or ask some questions of our speaker later on, you can do that via Twitter and we'll read those out. If you're at home watching, please ping us on hashtag sci-fi sci-fact and we will find you, and if your questions are good, we'll pose them to our speaker. But who is our speaker? Tonight's speaker is one of the most highly cited astrophysicists in the world. I didn't know that. Highly cited in the world. Professor Tamara Davis. She spends her days trying to figure out dark energy and why the expansion of the universe is accelerating, something I think we're probably all supposed to be concerned about. She's also an avid ultimate frisbee player. We all know what ultimate frisbee is. A bit. You may have to explain that as well. She holds a philosophy degree and is a huge science fiction fan. So please join me in welcoming Tamara, who will help us explore warp drives, light speed limits, event horizons, and perhaps even the ultimate fate of our universe.
Thank you. Thanks very much. It is my absolute pleasure to be here tonight to talk in this fantastic series, Science Fiction Meets Science Fact, which are, after all, two of my absolute most favourite things. I have to admit that when I first watched my first episode of Star Trek, I'm pretty sure I had no inkling that I would ever be standing in front of a group of people talking seriously about whether there was anything scientific about warp drives. But hey, science, it seems that real life can be stranger than fiction, and here we are, because that's exactly what is happening. Now, I also have to admit that I am not a Trekkie. That might be an embarrassing admission to be here. So I was fascinated by some of the details that I learned as I was checking up the history of the warp drives in Star Trek. And I also have to admit that I don't actually study warp drives directly. There's not many people in the world who actually do that. However, what I do study is cosmology. I study the expansion of the universe. I study stretching space. I study event horizons and black holes, try and measure the mass of black holes. I've measured time dilation in distant galaxies, supernovae, exploding stars, and putting all of those things together and attempting to use all of those amazing pieces of information that you get from the universe to understand the laws of physics and how they apply here on Earth. And yes, it does end up that that kind of thing is connected to how to build a warp drive. We'll get to that. Let's start with some history. Here is the first ship that did have a warp drive attached. It was the Phoenix, first flight in 2063. So we've got to get our act together because this is actually quite soon. The generator, the discoverer of the warp drive system is right here. This was the quote. This was the one small step for man, one giant leap for mankind type of quote. When the first warp drive moment occurred, it went something like and that was Zephram Cochrane, the inventor of warp drives on the first voyage of the Phoenix, which in this particular history I think was an old missile adapted from World War III. Yeah. So, what are warp drives exactly? Well, if you go into the Star Trek lexicon, and I had a fantastic time looking through some of these details, this Memory Alpha webpage has an enormous amount of information, but basically, the warp drive concept is anything, I'm going to call it anything that means that you can travel faster than the speed of light. Any propulsion system that makes you travel faster than light, which, as we know from relativity, could be a problem because Einstein's theory of special relativity says nothing can travel faster than the speed of light. But we will get to that. Anyway, the things that I'm not including as warp drives are things that are like a jump drive, which is you instantaneously end up somewhere without traveling through, and teleportation, that kind of thing, where you sort of just show up somewhere without traveling on the way. So that part I'm not counting as warp drives. So it's some sort of propulsion. Okay, now if you do look at this, these are the parts of the system that were required for the Star Trek version of the warp drives. And all of these have detailed information with sometimes schematics and all sorts of things. So go crazy, have a look at that. We've got what plasma conduits, the dilithium cores, magnetic interlock, deuterium cartridges, antimatter relays, all sorts of things. Now, most of this stuff is just the sort of techno-babble that they throw into Star Trek sort of episodes and a lot of science fiction to make it sound sort of vaguely scientific and futuristic. But we'll see as we go that where this connects with science fact. Of course, there are many other types of star things, including like Star Wars. Star Wars, they had the hyperdrive, not the warp drive. And according at least to Wikipedia, this is some collection of shows in which warp drives appear. So that's a very popular plot device. And as you can imagine, because it's very useful in science fiction to be able to have your protagonist still alive when they arrive at another planet that they're trying to visit. And also to make it not have to be an intergenerational sort of thing, and even just to be able to exchange messages in a decent amount of time with a distant planet. So extremely useful as a plot device. But why would you bother, really? And I've turned to Douglas Adams to help me out with this one. Warp drives are handy because, space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. You may think it's a long way down to the road to the chemist, but that's just peanuts compared to space. That's one of Douglas's more famous quotes. Another was this other one that I found was, in the beginning, the universe was created. That made a lot of people very angry and has been widely regarded as a bad move. So anyway, yes, space is big. This is one of the iconic photos of Earth taken by the Apollo astronauts from the moon. This is also a picture of Earth. Do people recognize it? Yeah, some people might know this photo, but it might not look like the Earth that you are used to, but that's because there's a big fat Saturn in the way. Earth is actually there. Can you see that? So that was taken by the Cassini spacecraft. It's one of the most distant pictures of the Earth ever taken. This is the most distant picture of the Earth taken, at least by humans. Thank you, Carl Sagan, I hear from the audience. Yes, this is known as the pale blue dot. There is Earth there. This was taken by Voyager. And Voyager, as you may have heard, was recently famous for having left the solar system. Now, it had sort of left the solar system a few times before because the boundary of the solar system is ill-defined. So it's like, yeah, I think we've left it. No, okay, no, now we really have left it. But now they really think that Voyager has left what's the sort of magnetic field region that's generated by our sun and is in interstellar space. Now, it's been traveling since 1977. Now, I'm going to date myself here, but I was 2 when it was launched. So it's taken a long time just to get to the edge of our solar system. That's not a different star, that's not a different galaxy, that's just local space. We need to do better than that. And indeed, you may think that Voyager may not really have even left the solar system in a way because the Oort cloud, which is where the comets are kicked into from, it will take Voyager still about 300 years to get there, and about apparently 30,000 to get to the outer edge of that. So space is big. Now, if this was a different kind of talk, I would then go and talk about all sorts of different types of propulsion that are being developed to get us out faster. Conventional types of propulsion, things like an ion drive or a solar sail that uses the radiation coming from the sun as and can put out a sail to propel spacecraft, things like that. But no, we're talking warp drives. We are talking faster than light. If we're going to go somewhere, we want to do it really efficiently. So let's see if that's possible. First question. Can anything break the speed of light limit? We are basically taught from infancy these days that nothing can travel faster than the speed of light. Einstein is on a pedestal. This is what special relativity says. That's the limit. So why are we even contemplating talking about warp speed? Well, the answer to this question might be complicated, but it is actually very simple. Yes. And in fact, now we're on to something that I did study during my PhD, this exact question. The things that can travel faster than the speed of light include things like expanding space. If you're falling into a black hole, space is stretching faster than the speed of light. Spinning black holes, wormholes, there are a variety of ways to go faster than the speed of light. But in every case, it is not something that's traveling through space. Nothing ever overtakes a photon on a path through space. It's space itself that is stretching in some way. So the question of can we break the speed of light is a difficult one, even if space can stretch faster than the speed of light. So let me go into a couple of these things in more detail, because this is where we start hitting the science. And this is actually what I did my PhD on initially, was the expansion of the universe and whether it can go faster than the speed of light. Ever since Hubble, we've known the universe is expanding, that velocity of distant galaxies is proportional to their distance from us. And this is actually really simple, and it's necessary if you want to maintain a homogeneous isotropic universe. So if you want something that is pretty much the same in all places and there's no special place in the universe, there's no center, then this has to be true. The velocity is proportional to the distance. That keeps everything in check. But if you go far enough, this implies that velocities must exceed the speed of light. And there's a lot of literature out there that actually was saying that, when you start to get far enough away, you have to do special relativistic corrections to the velocities that you're measuring in the expansion to make it fit with relativity. But you don't actually, because it's general relativity that is in force here, not special relativity. And in general relativity, space is an active ingredient. It warps, it bends, it stretches, and that is not limited by light speed. So if you didn't grasp the details of that particular thing, just remember that space can stretch fast and in any way it wants. It's not bound by the light speed limit. So that gets an interesting question, is can we see forever? And this is, I find an interesting thing to think about. If I shone a torch, I think of a laser pointer here, if I shone a laser up into the sky, in the absence of a ceiling and air and all that kind of stuff, if it didn't hit anything, would it travel forever? Would it reach an arbitrary distance? The answer, since we now know that the universe is accelerating, is no. It will only reach a certain far. And you might think that, hey, that a torch isn't big enough, maybe you want the sun, or maybe you want our galaxy. The question is, how far will light from our galaxy reach? And it won't go forever. There is a limit to how far we can see in the universe. That's known as the universe's event horizon. So if you're just trying to shine light through space, there's a limit not only to how fast we can travel, but also absolutely how far we can get, even traveling at close to the speed of light. So if we had warp speed, if we could go faster than the speed of light, we could break that limit and we could get potentially further. Okay, another way where you see things stretching, space stretching, moving faster than the speed of light, is when you fall into a black hole. And this is an artist impression of spaceships sort of plummeting into some sort of spirally black hole thing. And this is actually a terrible reproduction of what's going to happen. We like to think of black holes as like we draw a mesh and stuff falling in and space being dragged in, but it wouldn't actually really look two-dimensional like this. What you have is space is basically being sucked into the black hole, and light, as it's trying to travel out, is traveling against this sort of flow of space and being dragged back in. So black holes are famous for, well, sort of not being black, but having the property that light can't escape from inside the horizon. And so this is another situation where you have space stretching faster than the speed of light. It all sort of basically goes into an infinitely deep bucket with a singularity at the bottom. And that singularity is a problem. Anytime you get something like a singularity, it basically means your theory has thrown an infinity at you, and the theory is not good enough. There is something wrong, probably, with the theory. And we expect that to be true because we know that quantum effects should be important at the center of a black hole. And until we understand a quantum theory of gravity, we're not going to be able to explain this particularly well. And as you'll see, I think that one of the most important points we can make about warp drives is we're really not going to be able to figure out exactly how and if we can do it until we can understand a quantum theory of gravity. Okay, this is a bit more of a realistic simulation of what falling into a black hole might look like. If you are interested, go to Andrew Hamilton's website, which is a fantastic playground for looking at visualizations of black holes. And this is I'll let that website explain it to you if you get interested. Does anyone recognize this? No? Did anyone see Interstellar? There's a few unfortunately's from the front here. Yes, Interstellar, every time I go, a friend of mine goes and sees Interstellar, it seems I get a phone call or a Facebook message saying, "Hey Tam, I just saw Interstellar. What did you think about it?" And for those who haven't seen it, how many people have seen it? Quite a few. If those who haven't, cover your ears if you don't want a spoiler alert. The take-home message that I have from Interstellar is it is really bloody difficult to get to other planets, and they're pretty much guaranteed to be more sucky than Earth when you get there. So let's look after this planet, because it's way more difficult to do anything else. Anyway, this was the black hole that they went and visited in Interstellar, and they did actually spend some time and energy visualizing this black hole accurately, scientifically. And what you're seeing here is the black hole has an accretion disk, which is like the rings of Saturn, basically. It's material falling into the black hole, but like our solar system, it's formed a disk as it does so. And because of the incredible strength of gravity of the black hole, the light is being bent by gravity as it comes. So it's the back of the disk is being bent by gravity and coming over the black hole, and we're seeing this top bit here is the light coming from the back part of over the top of the black hole, and down the bottom we're seeing the same thing but from the bottom. So the light's being curved by the black hole so that we can see it from different directions, which gives this funky looking shape. Okay, so the other thing that where you get faster than the speed of light is in a spinning black hole. There's something called the ergosphere. You get sucked around. If you even traveling at the speed of light, you can't stand still. You would have to orbit with the black hole. So that's another place where you have faster than the speed of light. It was interesting that this was the more accurate version of the simulation that they did of what a black hole would look like, but it didn't quite look impressive enough. And so this was the actual black hole as it appeared in Interstellar. And the difference being that they took out some of the rotational effects. So if you take what this is the basic thing of what it would look like without some effects. Here it gets coloured because of the rotation. You get Doppler shifts, but you also get beaming. So if something's coming at you in relativity, it will look brighter than going away, and so you get a light and a dark side of the black hole. That's just an interesting tidbit. Okay, and finally, the thing that you're probably quite familiar with, wormholes, pipes through space. Can be an end of a black hole attached to another black hole, but the theory of whether you can actually have wormholes or not depends on whether the mouth of that attachment, whether, the black holes went down to a singularity, whether you can keep that mouth open and attached to something else that then comes out the other side. And if you can, what you would need to be able to do that is probably some sort of exotic matter in the center, something with negative mass or negative energy that could prevent a singularity forming. Now that's negative mass, negative energy is speculative, but and the biggest problem with that, but theoretically the maths works. And we're hesitant to say anything's impossible because usually when you say something is impossible, you're interrupted by somebody doing it. So wormholes make a shortcut through space. So they mean nothing overtakes a photon, but it just gives you a tunnel that means you can get from one place to the other by traveling a shorter distance. And that's been used in things like Contact and Stargate and these kinds of science fiction movies. So, things can go faster than the speed of light. Does that mean that we can make a warp drive? This is the question. And there's been a reasonable amount of work on this. The most famous one is the Alcubierre drive. And what happens in that particular version of a warp drive is that you basically create a bubble of space that moves through the other space and would take a spaceship along with it. So locally, the spaceship isn't moving faster than the speed of light, but you've made a bubble of space that does move faster than the speed of light. Now that sounds really odd, but the way that you might do that is by coming up with some sort of mechanism by which you can make space contract in front of your spacecraft and expand behind the spacecraft. And the mathematics actually works. Theoretically, this would be possible. These are the sort of the mathematical models that people have come up with in order to do this. Here you've got basically, this is like the slope of space where it's like compressed in front and expanding behind, and this would be the spaceship that's in there. You'd be sitting in this little football-shaped thing in the center, and the ring around it is the part that's actually generating the field that's causing the tilting of space and causing the propulsion from the warp drive. Now I should say, very speculative, and although it is a legitimate solution, again, in order to make this work, you need something like negative mass or negative energy, things that we don't necessarily believe exist, don't know if they could exist. But once again, until we really have a quantum theory of gravity, it's hard to say. So this is just an alternate version of the same metric. The convenient thing, there's a couple of convenient things about this solution, is that inside this bubble, space would be flat. So, and the time that the spaceship perceives would be exactly the same as the time outside the bubble. So there's a warp of space sort of in the bubble around the spaceship, but you have locally just normal clock ticking, boring time going on inside, the same as what would be happening outside, but this bubble would be moving potentially faster than the speed of light through space. Sound crazy? Quite possibly is. This is the analogy. It's sort of like you've put a local slope in space so that it's sort of like riding a wave. You're sort of riding a wave of space in a way here. I liked this little GIF. It keeps going so it looks like they surf forever. Appropriate analogy for Australians. Yeah, so can we ride the space wave and have a warp drive actually work? So biggest problem practically is that we need this negative energy thing. I took this slide from Harold White. This is actually research that is being funded by NASA. They have put effort into this. They've got a breakthrough propulsions sort of center where they give small amounts of money to interesting, high risk, high return type endeavors, and this is one. There's a variety of different mechanisms by which people can have suggested that you might be able to do this. Another one was Richard Ubusi, who has suggested that maybe we can manipulate the vacuum energy to do that. And I'm going to try and explain a little bit of that next, because going back to the stuff that I study the expansion of the universe and dark energy and dark matter, and whether we can understand what's happening with the universe with new fundamental physics here on Earth. So let me just explain that a tiny bit. Okay, ever since we discovered the expansion, actually, have people seen this photo before? This is Edwin Hubble doing two things at the telescope that we never do anymore. Can anyone think of what those two things are? Smoking and actually looking through it. Well done. Yes. Some of the romance has been taken away because we no longer look through the eyepiece in the telescopes. We sit in our bright lit, heated control rooms and watch the images appear on the screen. But here is Hubble. He's doing some work. He was only one of many people. Vesto Slipher did a lot of research that helped discover the expansion of the universe. Henrietta Swan-Leavitt is also probably underrepresented in the amount of work that she did there. But together, they discovered that the universe is expanding. Ever since then, people have wanted to know what's happening. What will the fate of the universe be? So all the galaxies are moving away from each other. Is that expansion going to slow down and stop and turn around and recollapse? Or will the expansion go on forever? There was very little doubt that the expansion would be slowing down, because we all know that what goes up must come down if gravity slows things down. Now, the question was only if I throw this controller fast enough, if I throw it more than 11 kilometers per second and there's no air resistance and no ceiling again, it will escape Earth's gravity and never return. It'll slow down as it does so, but it will still have enough initial velocity to escape. So this was the question: do the galaxies have the escape velocity to escape from each other's mutual gravitational pull, or is the universe going to recollapse? It took until the 1990s to be able to figure out the answer to this question, because measuring expansion is much easier than measuring how that expansion changes with time. It's a much more subtle effect, the latter. So this is probably a familiar story to many of the people here, because there's some locals involved. But basically, it needed the discovery that supernovae, these exploding stars, could be used as standard candles. And once you know, the standard candle just means that it's an object of known brightness. And once you know how bright they are intrinsically, you can look at them, look at how bright they appear, and figure out how far they are away. But because we're looking at really, really bright things, we're looking so far back in the past, or we're looking at things that happened billions of years ago. So we can look at how far they are away, and that tells us how long ago we're looking at them, and so we're looking at the universe as it was in its infancy. And then we add an extra piece of information, we get a spectrum, we measure the velocity of the supernova, and we put those two pieces together to look at the velocity of the universe as it was in the past and compare it to the velocity as it is now, and all along the way. And when that was done in the 90s, it was discovered that the expansion of the universe is actually speeding up. So the famous people around here, which hopefully many of you have heard of, Brian Schmidt from ANU won the Nobel Prize with a couple of his mates for discovering the acceleration of the expansion of the universe. And so the reason that is bizarre is that that's very similar to me gently throwing this up in the air and watching it accelerate off into space. What we've discovered with that discovery is that there is some repulsive force coming due to there's something out there that has anti-gravity properties. And the leading contender for that is vacuum energy. Now, vacuum energy was predicted by quantum physics to exist, and it's been measured in some ways. But basically, it is something that has negative pressure. And that is akin to having negative energy. And therefore, the stuff that's accelerating the universe might also be harnessable to make warp drives. So there's a nice sort of circularity in this. The reason that we're doing this kind of research is so that we can understand the fundamental physics that goes behind these things, so that we can then perhaps do things like create warp drives. And we don't know whether we're going to be able to do that or not, but that's one of the motivations. Now, I was just talking very theoretical and warp drivey, so I'm going to give you an exercise, a picture that's much easier to think about for a second. I joined the supernova teams and Brian Schmidt's team after I finished my PhD, after I'd finished studying the expansion of space, and he recruited me to try and apply that to the supernova studies. I joined a team called ESSENCE, and with ESSENCE we spent 6 years scanning a few regions of the sky, and over that time we discovered 200 supernovae and used those to confirm the original discovery that the expansion is speeding up. Now, this is one of the images from the ESSENCE survey. It was actually half of one image. We took 32 of these each night. And if you look at this image and you sort of zoom in on a little patch, say about that big, you have something that looks like this. Now, how do you find supernovae? They're exploding stars, they're transitory events. And so you can't plan an observation because you don't know when one's going to go off. But if you just look at large enough pieces of the sky, statistically, you're likely to find one on any one night. Now, a supernova will go off in a galaxy once every 400 years or so. So if you observe 400 galaxies every night, you'd see one supernova per year. So we wanted to find one a night, so we had to observe many, many more than that. And all you do is basically you go back to the same patches of sky, observe them again and again, and see if something changes. So this is one of the cases where something changes. Here you have the before picture. There is no supernova in this. Here is the after picture. There is a supernova in that. Can someone point out the supernova to me? Anybody? Feel free to talk amongst your neighbour. Point at something. I'm going to come with a laser pointer and... Down the bottom. Down the bottom? Here we go. So this button here is the laser pointer, the top one. Down there? Oh no, that's a great guess, but you can see that they do look different, but the before image is typically a bit better than the after image. So you've got to take into account the fact that the before image we choose is one that's got really good conditions, and the after one might not be as good. Anybody else? Who wants to take a guess? I see a couple of people pointing. You're come on. Yeah, this one. I saw you pointing. You must have been pointing at something. The top button. Yep. Oh, that's also a great guess, but that's in the before picture and not in the after picture. So that one, it is there, but it's not there. So it should be in the after picture, but not in the before picture. Okay, someone else help me out. Yes. top button there.
Are you thinking that this is rounder, this is more elongated,
Yes.
which means the flash is blinding the top and bottom?
Yes, that is more rounded in the after photo than here.
Because it's a crappy photo.
Because it's a crappy photo, yes. That's not the supernova either. Okay, 2 more tries. Who else? Someone up the back. Do you have a good guess? Yeah, do you know anyone? Did you want to point something out? Here we go. Top red button there. Oh, no, again, that's the fuzzy one in the before picture. Yeah. Oh, here. Red button there.
Red button there. Is it that little dot there?
No, unfortunately that's not it either. I'll put you out of your misery. It's actually really difficult to see. It's there. Can you see a little tiny blob at the bottom of that fuzzy patch? I love putting this up because this demonstrates, I usually have a title on this slide, why this is hard. This was why this is difficult to do and why we really needed armies of PhD students to look at these in intricate detail. No, I'm kidding. Why we needed software that could do this automatically. So and this is actually one of the things that Brian Schmidt did that got him the Nobel Prize was actually design some software that could subtract one image from another accurately and see the differences. So in here, there's actually 2 things that significantly change. One is an active galaxy at the center where you have the black hole at the center is changing the brightness and therefore it changes in brightness. And then this dot up here, which is the supernova, which can be subtracted from the galaxy light once you blur the image to the same resolution and all that kind of thing. So that's it. That's the supernova discovery, and that's why it needed to wait for really big telescopes and digital cameras before we could really make this discovery. But now we've got something new about the universe that we're trying to understand. And although it's hard to find supernovae, we've become very good at it. After ESSENCE, I was part of the Sloan Digital Sky Survey, supernova search. Here's 500 examples of supernovae that we found there. Here's like a couple of baby snaps. The blue dot is the supernova. They're the galaxies. Aren't they cute? And again, we confirmed that the expansion of the universe is accelerating. We don't know why. What could the dark energy be? And can we use it? This is the question. So the energy, it's a quantum physics effect where the vacuum itself has some energy. The virtual particle pairs pop in and out of existence all the time, partly because the Heisenberg uncertainty principle says you can never know where something's position and momentum is exactly, nor can you know its energy and its duration exactly. So you don't violate conservation of energy if you only appear and then disappear immediately. So in a way, virtual particles, you could say, are borrowing energy from the universe to exist briefly and then disappear. And that's how you can end up with negative energy. The Casimir effect is a really interesting one. What happens is that you try in perfect vacuum, or as perfect as you can get, put 2 metal plates close together, and when you do that, it restricts the modes that can form in these virtual particles, and you end up getting a relative pressure between the restricted part between the plates and the normal vacuum outside the plates, and that ends up pushing the plates together. You can do an analog with water waves. There's a little video showing this, that if you put a couple of little plates down into water and you start the whole tub vibrating, the types of waves that can form between the plates are more restricted than the wavelengths that can form outside the plates, and you end up getting a water pressure that pushes the plates together. And so the analog in water is what they think is happening in the Casimir effect for vacuum energy. So that's something where you can sort of get a negative energy. And this vacuum energy that could be the thing that's accelerating the expansion of the universe as well. So how are we attacking this question now? Well, we've started a new survey to try and do what the dark energy could be. This is a much, much bigger image than the ones that we used to do with ESSENCE, even though it's actually on the same telescope. We've just put a much, much better camera. We've got a 570 megapixel camera on here now. And this is one of the images that you get in a single exposure. Each of these is different little digital cameras. And if you zoom in on one of these, it's a charge-coupled device. If you zoom in on one of those, it looks a bit like that. So you can see the amazing resolution that we get across the whole field. So we've got our mates in Chile are taking these images. Meanwhile, in Australia, on the Anglo-Australian telescope, we take spectra of objects in these images. We've got a device called 2DF, which puts optical fibers at the positions of galaxies of interest and supernovae and that kind of thing. And you can get spectra of 400 at a time. So we can measure the velocities of these things, measure the types of supernovae, the types of galaxies. And now the original discovery of dark energy was made just using 52 supernovae. With our survey, we're actually going to measure over 3,000 supernovae over 5 years, so a much bigger sample. We're going to measure dark energy in detail and be able to see whether it changes with time, which is one of the first things that you need to be able to do to be able to figure out what it is, whether it can be vacuum energy or whether it has to be something different. So this is actual real data here. We're 2 years into a 5-year survey, and this is the parts of the universe in purple here that we've actually surveyed. Here is like one of the data cones that we have, just showing us a very small sample of our data. And just to give you a sense of scale, the galaxies that we're looking at here, halfway down, so the observer, our telescope is down at this pointy end, the galaxies there emitted the light that we're now seeing about 8 billion years ago. So to put that in perspective, the Earth is 4.5 billion years old. So that light was emitted before the Earth even formed, which is really astonishing. And when you're at the telescope and you were observing these things, it feels really exciting when you see that sort of data come in. Now, way back there, the extent of our survey goes to about 12 billion years ago. And that's almost getting back to the age of the universe, which is 13.8-ish billion years ago. And so there's the age of the Earth approximately. The stuff that emitted the light there was emitting the light at the same time the Earth was forming, and we're just seeing it now. So that gives you a sense of just how far we're able to see with modern telescopes. And I'll skip over this because we've been going for a little while now, but we're also measuring the black hole mass of supermassive black holes at the center of about 500 galaxies out to a great distance. And we do that in a really cool way by measuring the timing of variations in the center compared to variations of light reflected from clouds outside of this. And that time difference gives us the mass of the black hole with a couple of other details. Now, you may be familiar with these active galaxies that have supermassive, that the supermassive black holes in the center are sucking in material. They often look like this. The radio jets come out of them and spew out of the poles. And here is a Hubble Space Telescope image of an active galaxy. But notice that the resolution here is about 400 light years across. So it takes light 400 years to travel across that distance there. But what we're able to see, because we're looking just for time variations, we can resolve things that are only like months across. So the very center of this is what we're looking at, and how we're able to measure the black holes at the center, which is sort of cool. So to finish off, let's build a warp drive. People have gotten very enthusiastic about this and done extremely detailed models, things like this, where you show how you've put this ring around that's generate the warp bubble and the spaceship is inside. You've got schematics. You can go and look at this in intricate detail. Might be getting a bit over-enthusiastic for the current state of the technology, but you know. If we start a bit smaller, the experiments that are being done are things where they're basically trying to see if they can generate something akin to a warp field, and it would be able to be measured by looking at an interferometer and seeing that the path length through space has been different through different arms of the interferometer if you've got this warp field generator on here. When I was reading about this, it was not clear to me at all about how they were going to make even a sort of mock-up of a warp generator here, but it is actually something that people are trying to do. I've already mentioned some challenges, energy requirements. Maybe you need more mass than the observable universe. Some people say that you only need 3 masses of our sun. Some people say mass of Jupiter, maybe only the mass of something like Voyager. So, and it all needs to be negative mass, so yeah, maybe. You might need train tracks, you might need infrastructure where you can't generate this bubble yourself, it has to be there already and you surf down it. It might be that you can't survive inside it because the Hawking radiation, the same kind of stuff that comes off black holes is going to fry you. It could be that the destination gets fried because as you arrive, there's basically akin to a sonic boom as you break the sound wave, but it's an optic boom as the light gets in. So you might not want to be friends with anyone that you're visiting because you might obliterate them. And yes, it needs a quantum theory of gravity. And what talk like this would be complete without mentioning that, yes, you would also get time travel paradoxes if you could travel faster than the speed of light, which might be a problem. But, you know, I stopped my parents from meeting or something like that. That's a whole other talk in itself, whether that's actually a problem. But one final thing I will note is that, you know, Marty McFly had the hoverboard. It may still be possible to create this sort of thing with the same sort of negative pressure, whatever's causing the acceleration of the expansion of the universe. If we can harness it, maybe we can make the hoverboard things, which is something that people do keep asking me for. Okay, this is my absolute final slide. This is an image, one of my favorite images. It's the Hubble Ultra Deep Field taken by the Hubble Space Telescope. Are people in the crowd familiar with this one? Few people seen it? This is a picture of empty space. This is what you get when you take the Hubble Space Telescope and you point at a blank piece of sky and you leave the shutter open for 11 days. As you collect more and more photons, faint galaxies that you had not seen before appear on your image. And this is what you see. It's a beautiful image with enormous numbers of galaxies in there. Basically, every dot you see is another galaxy, something like our Milky Way. Even the little tiny dots. There's like a couple of stars, like this one here. If you see the cross, that's a star, but everything else basically is a galaxy. And this, remember that I said that we can't see forever? In the universe, that there's a limit to how far we can see. That's because the universe is accelerating, and that means that space is going to be expanding fast enough that light can't travel everywhere. Now, the distance, which is at our event horizon at the moment, is a redshift of 1.7. And I haven't explained redshift, but the most distant galaxies here are at a redshift of over 6. And that means that most of the dots in this picture are galaxies that we cannot communicate with. Most of them are so far away that although we've seen them as they were in the past, we will never be able to, the universe has expanded too much and sped up too much. We're never going to be able to signal back, and they're never going to be able to signal to us. We're never going to see them as they are today. We're looking at them as they were billions of years ago, and we've now lost contact. So, if we can invent warp drives, that's the only way that we're going to be able to go and visit them. So let's see if that's something that we can possibly do in the future. Who knows? Thanks very much.
I don't even know where to begin. Does anyone have any questions, and let me phrase that carefully, that could possibly be answered within the next 10 minutes or so and give anyone else an opportunity to ask another question? One down the front, sir, then in front of you.
That picture.
Yes.
Why have the stars got crosses on them?
That's just a part of the optics of the telescope. And it arises because the stars are point objects. They're so small that they're really just a dot, and they're not extended. And that, the transforms that you get as you go through the optics results in the crossbeam.
So it's not a fancy lens that makes it look more romantic?
It's not a fancy lens that makes it look more romantic. Actually, we try and get rid of those because because if it's a really, really bright star, that vertical light that has spilled out like this goes and gets in the way of all the galaxies that we really wanted to see. So sometimes that can destroy images because of that effect.
And how fast can the warp bubble travel?
So I did look at, there are different, how fast can the warp bubble travel? There were different predictions. The original version didn't mention any limit. The one that was trying to use quantum gravity said that there was a limit of 10 to the 32 times the speed of light, if I recall correctly. Now, basically it means you can, very fast, yes. But again, when you're talking about numbers like that, you really have dived into rampant speculation. We don't know. Yeah.
We had a question behind, but first we have a Twitter question, is that right?
Oh.
Yes, we do. This is asked by Jenny at catwatt1. She asks, what would you be able to see out of a warp bubble at surrounding space to know when you get there?
That's a really good question. I'm not entirely sure. There was, I should have read this. There was, I think Grant Lewis and one of his students from University of Sydney actually looked at some of that, and so maybe we should look up that as a possible solution. But particles do apparently pass through, just like when you're looking at that video of a wave. There's like little shrapnel and stuff in the like seaweed or something in the water that will just sort of bump over the wave as the wave goes past. And so stuff does pass through the bubble, but I don't know any more details than that, I'm afraid, sorry.
Once again, looking at that picture up there, has anyone ever looked at that sort of thing long enough to spot stars dropping off from our visibility? They're at the event horizon, effectively.
So that's a really good question. So when I say that you can't, like, there's an event horizon here. So what happens is you never actually, we'll never see them disappear. Just like when you're watching a black hole, you never see something fall into the black hole, because it gets excessively time dilated. The light that's traveling from near the surface of the black hole takes longer and longer to get from near the surface to us as the emitter gets closer and closer to the event horizon of the black hole. So they never actually disappear. You never see them go, oh, they're over the event horizon now. It gets longer and longer, more and more time dilated, so they look like they're moving slower and slower. And they get redshifted, so the wavelength gets stretched until they become invisible. And the same thing, exactly the same thing will happen to the galaxies. We'll always continue to be able to see them. We'll just see them as they were longer and longer in the past. We'll never see them as they are today, but we'll see them as they are longer and longer in the past. Actually, I have the actual plot that I can show you, but we won't go into this in particular detail. But you see them longer as they were longer and longer in the past. I'll ignore this. Go back and look at that if you want. And they never actually disappear. So you can never see something drop over the event horizon. You'll just never see it as it is today. Does that make sense? And the redshifting of light, the stretching of light, is one of the ways that we can tell things are moving away from us. But it's also will mean that those galaxies will fade into invisibility, and we will lose them that way, as opposed to any poof, they're gone, instant.
Anyone else up the back, down close? Can I ask, is there anything that completely confuses you from this world, or are you just all across it?
That's all easy, right?
Just so simple?
No, there's plenty of stuff that's very confusing, and especially some of the getting your head around the warping of space and all the different distances and expansions and who sees what, and the time dilation paradoxes and stuff.
So you've got a lot of headaches at work, I'm assuming. It's
so much fun though. You get to go to work each day and work out like problems about time dilation and figure out ways that you can actually go and measure it, and try and go to work and try and figure out some way to discover something new about how physics works, and then bring that back and make hoverboards. So, every day is awesome.
How do you know that there is a finite beginning of the universe? Because it seems like it tends to be like you can only see how far you can see, but if there was something beyond, you wouldn't be able to see it anyway.
I love your question.
So how do you know it hasn't gone for an infinite a time? And then I'm starting to think, well, could space bend around so that where it originated from is the actual 360-degree horizon? If that sounds... I write science fiction books, so...
Yeah. Let me see if I've got something here. I thought it might be in here. Oh, yeah. Okay, hold on.
Plugging straight into Hubble now, I see.
Here. Okay, so that's a fantastic question. So when we were looking at that image that I just removed, we can look the most distant galaxies that we see in that image emitted the light about 13 billion years ago. So that's really close to the 13.8 billion years that we think the universe has been around for. We think that because of the rate of expansion at the moment and how much acceleration and deceleration we've been able to measure. You can trace that back and find the time when all of those galaxies were sitting on top of each other. At that time, of course, galaxies wouldn't have existed yet. So you've got this age of the universe, which is mostly based on how fast the universe is expanding now and our understanding of the acceleration and deceleration in between. There's a prediction that was made. First, that those galaxies that we see, if we kept the shutter of the Hubble Space Telescope open for longer, observed for another 11 days, and just piled up more and more light, we wouldn't continue to see galaxies. The reason is that we're now looking so far back in time that the telescope's looking back to the time before galaxies had ever formed. And so the number of galaxies that you see will drop off, and the type of galaxies that you see has evolved over that time. So you can tell the difference that way. But if the universe was once really compressed, in a really hot, dense state, then that means that as you put all this matter and stuff together, it must have been hot, it must have been dense, and it would have been glowing. And the prediction was back in the 30s, I think, that you should be able to see the radiation left over from that really hot, dense epoch in the universe. People in the 60s saw this microwave background radiation that was basically the same everywhere they looked in the sky. And they thought it was bird crap in their telescope or something like that. They tried to get rid of it, couldn't get rid of it in any way. It turns out that radiation was the afterglow from the Big Bang. So it's evidence that the universe was once in a hot, dense state. And not only that, there's more. If it was that hot and dense, it means that sound waves would have been traveling. And in fact, if you do the calculation, their sound waves are traveling at more than half of the speed of light. You can calculate, just based on the normal physics that is how sound is traveling to your ears in this room, and the normal gravity about how I jump up and fall down, how sound waves would have propagated, and that they would have formed a pattern. That pattern is not random because of the distance that light, or that those sound waves could have traveled from the Big Bang to the point where the universe became expanded enough that sound couldn't travel anymore. So it became so dilute that the sound waves had nothing to bounce back off. It's a prediction of a pattern. That pattern was seen by 3 different telescopes measuring the microwave background. Here is one, that was the WMAP telescope. This pattern is what was predicted by the WMAP telescope. Let me see if I've got actually the thing. Oh, yes. This was the pattern that was measured by the Planck telescope. You don't need to know exactly what the details are, except that it's how intense that pattern is as a function of separation. So it's basically, if you've got a hot spot in the microwave background there, do you expect another hot spot there, or would it be a cold spot? If there's a correlation at a particular distance, you get a peak. And this is the pattern that they predicted, based on the amount of dark matter that we know from galaxies, the amount of dark energy that I was talking about from the acceleration of the universe. And that's what you would predict if there was no dark energy, so if the universe wasn't accelerating. And that's what you would predict if there was no dark matter. So the dark parts of the universe that we're studying, that were sort of the topic of this talk, what are the quantum effects, are confirmed in this sort of data as well. And so, sorry, that was an exceptionally long answer but it was a really well-posed question. And we've now detected these waves not only in the microwave background, but also in the distribution of galaxies that formed from those initial patterns.
Patient gentleman with the microphone.
The speed of sound, light is the basic speed you use for everything, but CERN accelerator in Switzerland apparently reckon they've gone faster than the speed of light. How is this going to affect the whole history of looking at the space and getting our places?
I'm not sure if what you're referring to is a thing that they did with neutrinos a couple of years back, where they thought that they had detected some neutrinos that were travelling faster than light. What they had detected was a glitch in one of the screws that wasn't put in properly to the detector, and that result has since gone away.
Sounds like it screwed them up.
Twitter question? Kylie.
I'm asking another question from Twitter, thank you. It's at Daniel Rucker asks, why is the speed of light so slow relative to the size of the universe?
That's a really good question. I don't know. It could have been different, but if it had been different, the strength of the interactions in atoms, like the light is the carrier of the electromagnetic force, so the strength of electromagnetic interactions would be different. You might not have, it might mean that chemistry wouldn't happen as we know it. It might mean that stars wouldn't have formed, radiation pressure would be different. So it might be one of these things that it was required in order for observers to be here. That's one possibility, yeah.
Question up the back middle. How many more can we take, officials of the Academy? 2. Is this one? Sir. And then there's one over to my right.
Yeah.
Can I cheat and ask 2 questions?
Is that one of them?
The first one is, if the black hole, or not the black hole, but the beginning of the universe began in a massive explosion, it couldn't have, because the universe must have been there before it exploded.
Is that a question?
Yes.
There was the modern understanding of the initiation of the universe is that we used to say, you know, time and space were created in the Big Bang. And in a sense that might be true, but it's assumed that there was probably something before. And the leading contender for the spark is one of these quantum fluctuations that I was talking about. It's all amazingly interrelated. If we could only understand that quantum theory of gravity or something, we would have a much better understanding. But it's possible that there was one of these small fluctuations that I was talking about that sort of borrows energy from the universe, did it in such a way that it caused an inflation that generated the universe. And you can actually do that sort of with conservation of energy, because you've got kinetic energy and potential energy balancing if you do it in a hand-wavy way. And yeah, I'm not being very precise here, but I agree, or most physicists would agree, that the leading contenders for what could possibly have started the Big Bang all have some pre-existing something, quantum foam or something like that, but not necessarily time and space as we know it, which may have been dimensions that were generated in the Big Bang.
And if I can have the second question, which is very short, was when Brian was here giving his talk a couple of years ago, he was asked the question of, what of it? And the basis of what are you doing that is for the benefit of mankind?
So I guess you get those sort of questions a lot here. I like to think that, part of the reason I'm doing it is because, I have a variety of answers here. Part of the reason I do it is because it's beautiful. It's the same reason that people do ballet or listen to music. But there's more than that. It has enormous practical benefits. So hopefully we can figure out what dark energy is. Maybe it's something that can give us a clean type of fuel for humankind, a new type of propulsion, as we've been talking about, something that will help our technology and feed the billions of people that are going to be overpopulating the planet. But in the interim, that's like a pipe dream. That's the ultimate thing. But in the interim, you get a lot of useful spin-offs on the way, and a lot of the efforts that we make to try and get the last tiny photon from a distant galaxy are things that develop cameras that are now being used in medical imaging, for example. People who are trying to discover black holes by looking at rapidly varying radio signals invented Wi-Fi. And just there's a whole series of things that where we, by trying to push the bounds of our understanding in physics, we're also pushing the technology that we use to be able to do that, which improves the capabilities of what humankind can do.
I'm convinced. You can keep my taxes. Last question.
I struggle with my question, but if I shine a laser light up into the sky, I presume photons are moving at the speed of light. I wonder if we could exceed the speed of light by giving a push at the start end so that the actual photon appearing coming out at the distant end seems to go faster than the speed of light. There is an analogy in, if I get a Duracell battery and connect it to a piece of copper wire, I think the electricity, the electrons appear to flow at maybe the speed of light or something very, very fast. But I understand what actually happens is that an electron starts at the beginning and shuffles them all along. The electron doesn't actually move fast, it just appears to be fast because one goes in at the beginning and another one shuffles off at the end, giving that appearance.
Yeah, so it's like a sort of like a series of train cars getting pushed at one end, going.
Well, if photons do that, maybe we can exceed the speed of light.
The analogy, I think, breaks down, unfortunately. There are things like the phase of a wave, a light wave can move faster than the speed of light, but not the information carrying part of the wave. And so most of the analogies with things like sound, which is anything where you have something bouncing off something else, tend to break down when you start talking about light and the light speed limit. But I'm happy to say that there's always, we've been talking about speculative stuff all night, so who knows? Yeah.
Great way to end that, I think. Who knows? Before we thank Tamara, we also need to acknowledge that she is the Australian Academy of Sciences 2015 Nancy Millis Medalist, which means she's a women leader in science. You are the woman leader in science.
Thank you.
But now clap louder to say thank you very much for mind-blowing and awesome talking.
Thank you. Thank you very much to the Academy as well for that.
And can we also say cheerio to our people online and let you know that this talk will be shortly available on the Academy's YouTube channel. Also, please note that this coming June's talk is cancelled. So the next talk will be in July with Professor Barry Brook, who's going to talk about the next big techno fixes for climate change. So the place, I hope, will be packed for that one. Thank you all and enjoy your evenings.
No worries.
The second to last question about what use is it?
Yes.
Ernest, I don't know if it's